is a canvas upon which the universe paints its most astonishing creations. We look up into the inky blackness and perceive a staggering tapestry of celestial bodies, each a testament to the complex, relentless laws of physics and chemistry. Before we continue, please like and subscribe. Among these countless distant worlds, the existence of exoplanets has fundamentally reshaped our understanding of cosmic evolution. These planets orbit stars beyond our own sun, worlds that exist outside the familiar confines of our solar system. The search for these distant neighbors is no longer a niche pursuit. It is a central endeavor of modern astrophysics. We are no longer confined to observing the familiar dance of the planets orbiting our star. Instead, we are peering into the atmospheres of alien worlds, attempting to decipher the processes that govern their very existence. The prevailing theory for planetary formation, once anchored in the familiar mechanics of our own solar system, began to confront the sheer diversity of exoplanet systems. Our initial models, based on the accretion of material from a protoplanetary disk surrounding a young star, provided a foundational framework. This framework suggested that planets form through gradual gravitational collapse and the subsequent clumping of dust and gas. Material in the disk would concentrate, gradually increasing in density until it coalesced into planetary bodies. This process, we understand now through the lens of stellar nurseries, is an intricate interplay between gravity, thermodynamics, and fluid dynamics operating on immense scales. However, as the census of exoplanets grew, a significant tension emerged between the theoretical predictions of these formation models and the observed reality of the planetary populations. The distribution of planets we find does not always align neatly with the smooth, predictable outcomes suggested by the simplest models. We observe planets in locations and configurations that seem to defy easy explanation based solely on the standard core accretion scenario. This discrepancy signaled that the mechanisms governing planet formation must be more nuanced, incorporating factors we were not initially accounting for. The first major turning point involved the recognition of the limitations inherent in the core accretion model. When applied across the entire spectrum of observed exoplanet demographics, core accretion posits that rocky, terrestrial planets form relatively close to their host stars, where the material is dense enough to allow for the slow accumulation of heavy elements. This model successfully explains the formation of our own inner solar system. Yet, when astronomers began to study systems with widely spaced orbits or planets orbiting very distant, cool stars, the predictions began to strain against observational data. The formation of gas giants, for instance, requires a massive reservoir of gas to be available early in the system's evolution, and the efficiency of this process seems highly dependent on the specific characteristics of the host star and the surrounding disk environment. A parallel and equally compelling line of inquiry focused on alternative formation pathways. The concept of gravitational instability offered an alternative mechanism for rapidly forming massive planets, particularly gas giants, in the early stages of a protoplanetary disk. This theory suggests that if a region within the disk becomes sufficiently dense, its self-gravity can overcome thermal pressure, causing a rapid, catastrophic collapse that forms a giant planet directly, rather than through slow, stepwise accretion. This mechanism provides a pathway to explain the existence of extremely massive planets, and potentially the very wide-orbit giants that are sometimes observed. The interplay between these two primary theories, core accretion and gravitational instability, became central to understanding the diversity of exoplanetary systems. The resulting picture is not a single, monolithic process, but rather a spectrum of possibilities dictated by the initial conditions of the stellar and protoplanetary disk. The mass, orbital distance, and atmospheric composition of an exoplanet are therefore not random occurrences, but rather fingerprints left by the specific physical conditions present during its formation. The implications of these competing theories extend far beyond mere cataloging. They force us to reevaluate our understanding of stellar evolution and the physics of accretion in extreme environments. The details of how planets acquire their atmospheres, how they migrate within their systems, and how they evolve over billions of years are all intimately connected to the initial conditions set during the formation phase. If we can accurately model the formation process, we gain profound insight into the fundamental processes that shape the entire cosmos. The observational evidence continues to refine this theoretical landscape. The detection of planets in the ice line, where volatile compounds can condense into solid form, provides crucial constraints on the initial thermal structure of the protoplanetary disk. Furthermore, the study of planetary systems orbiting M-dwarf stars, which are significantly cooler and smaller than our Sun, introduces new complexities. These stars have different accretion rates and stellar winds, which would inevitably alter the conditions under which planets form around them. The resulting exoplanets in these systems present a unique laboratory for testing formation theories under less familiar physical regimes. The concept of planetary migration also emerges as a critical consequence of these formation theories. If planets form far from their final observed positions, some mechanism must have acted upon them to move them. Tidal interactions with the host star, interaction with the surrounding disk material, and gravitational scattering among multiple forming bodies are all proposed as potential drivers of this orbital rearrangement. Understanding migration is essential because it connects the initial conditions of formation to the final architecture of the system we observe today. Search for the most extreme exoplanets pushes these theories to their limits. Worlds orbiting in the chaotic, distant regions of the galaxy, or those existing in highly eccentric orbits, challenge the notion that formation is a smoothly progressive process. These outliers suggest that the initial conditions, the density fluctuations, the magnetic fields, the initial angular momentum must possess a greater degree of stochasticity than previously assumed. They imply that the formation process is inherently sensitive to minute variations in the initial conditions of the stellar nurseries. The future of exoplanet research hinges on bridging the gap between the theoretical predictions and the high-resolution observational data we are gathering. Next-generation telescopes are designed to probe these faint worlds with unprecedented detail, allowing us to measure the masses, radii, and atmospheric compositions of these distant entities with greater precision. Each new data point acts as a constraint, either validating existing models or forcing a radical revision of our understanding of gravitational physics and plasma dynamics in the context of stellar formation. Ultimately, the story of exoplanet formation is a grand narrative about emergence. It is the story of how complexity arises from simplicity, how raw physical laws translate into the intricate architecture of worlds. We are moving from a simple understanding of planetary building blocks to a sophisticated comprehension of cosmic alchemy. The exoplanets that defy simple classification are not anomalies. They are the crucial evidence that the formation process is far richer, more dynamic, and more multifaceted than our initial, comfortable models suggested. They demand a deeper, more holistic theory capable of accounting for the astonishing diversity scattered across the night sky. This transition from theoretical competition to observational constraint reveals a landscape where the theoretical frameworks of core accretion and gravitational instability are not mutually exclusive, but rather complementary, each dominating different regimes of planetary system architecture. Challenge now shifts from selecting the correct formation mechanism to developing a unified theory that seamlessly incorporates both, recognizing that the initial state of the protoplanetary disk dictates which pathway is most likely to dominate. Consider the role of angular momentum transport within these disks. The mechanism by which material moves or fails to move dictates the local density profiles, the temperature gradients, and crucially, the efficiency of accretion versus gravitational collapse. Magnetorotational instability, driven by the magnetic fields threading the ionized plasma of the disk, is a leading candidate for transporting this angular momentum outward, allowing matter to spiral inward and build up planetary cores through accretion. If this transport is highly efficient, it favors the slow, gradual buildup described by core accretion, allowing planets to form in the cooler, more stable regions of the disk. However, if magnetic fields are weaker, or if the disk possesses a different magnetic topology, the dynamics can shift, allowing local regions to become gravitationally unstable and initiate the rapid collapse characteristic of gravitational instability. The transition between these two regimes from slow accretion to rapid collapses, likely governed by the interplay between thermal pressure, magnetic field strength, and the initial density fluctuations within the disk. Let us delve into the atmospheric implications, as the formation process dictates the initial composition of the planet. The material available for accretion is not just the bulk gas and dust, but the chemical inventory, the condensation sequence within the disk, governed by the temperature profile, determines where water, methane, silicates, and iron condense. Planets forming in the colder outer regions, beyond the ice line, are fundamentally different. They accrete solids from a reservoir where volatiles are locked up as ice, and their atmospheres are dominated by these frozen materials. Conversely, planets forming closer to the star, where temperatures are higher, can retain significant amounts of lighter elements, leading to the formation of hydrogen-rich envelopes, the hallmark of gas giants. Subsequent atmospheric evolution, the process by which these initial material inventories are processed, is profoundly influenced by the stellar irradiation and the planet's orbital history. For planets orbiting M-dwarfs, for example, the intense stellar activity, the frequent, powerful flares and stellar winds imposes strong constraints on atmospheric retention. These energetic events can lead to significant atmospheric erosion or photoevaporation, potentially stripping away the envelopes of close-in planets, forcing us to reevaluate the timescales over which atmospheres can be sustained, and thus how we interpret the observed atmospheric compositions of these systems. The concept of planetary migration, as previously introduced, moves from a mere consequence to a central, active component of the formation narrative. The process of disk-driven migration, where a planet interacts gravitationally with the surrounding gas and dust, is a continuous, dynamic process. Type I and Type Roman II migration describe how a planet's orbital radius changes as it exchanges angular momentum with the disk. The efficiency of this migration depends sensitively on the disk's viscosity, how effectively angular momentum is transported. If the disk is highly viscous, migration is rapid, potentially explaining the observed orbital spacings in some systems. If the disk is more laminar, migration is slower, allowing for more complex multi-body interactions to shape the final orbits. Furthermore, the process of tidal interaction with the host star, especially in systems with eccentric orbits, can induce further orbital evolution, driving eccentricity and potentially leading to the scattering events that populate the highly eccentric orbits we observe in some systems. This migration is not a single event. It is a continuous feedback loop between the planet, the disk, and the star, weaving the initial formation conditions into the final orbital configuration. The search for the most extreme objects, the rogue planets or those in highly eccentric orbits, pushes us toward understanding the physics of gravitational scattering in the context of the galactic environment. These outliers suggest that the initial conditions of the stellar nursery were not perfectly uniform. The stochasticity we seek is imprinted in the initial density fluctuations of the molecular clouds, the initial magnetic field configurations, and the initial angular momentum distribution of the collapsing protostellar core. If we view the formation process through a statistical lens, The diversity of exoplanets becomes a manifestation of the probability distribution of these initial conditions. The existence of planets far from their stars, or in highly inclined orbits, necessitates an understanding of gravitational dynamics on scales that span from the local circumstellar disk to the wider galactic environment. The gravitational influence of distant stellar companions, or even the gravitational field of the galactic tide, may play a subtle, yet significant, role in setting the final, long-term orbital parameters of these extreme systems. Next frontier in this understanding lies in high-resolution simulations. We are moving beyond idealized, one-dimensional models of disk evolution to fully three-dimensional, magnetohydrodynamic simulations that attempt to capture the turbulent, multi-scale physics of accretion. These simulations must accurately model the nonlinear coupling between magnetic fields, thermal energy, and gravitational collapse across vast ranges of scales. From the scale of the stellar surface down to the scale of the planetary formation zone. Success in these simulations will require better physics for the very early stages of stellar and disk evolution, particularly concerning the role of magnetic braking and the feedback mechanisms between stellar winds and disk evolution. By refining these simulations, we can begin to map the phase space of planetary formation, identifying the specific initial conditions that lead to the observed population statistics, thereby transforming the descriptive science of exoplanet demographics into predictive physics. The ultimate goal is to create a universal algorithm that can take the initial conditions of a stellar nursery and predict the resulting architecture of its planetary system, turning the bewildering scatter of exoplanet data into a coherent, predictable map of cosmic emergence. This pursuit of a universal algorithm demands an unprecedented level of fidelity in our physical models, forcing us to confront the limitations of current computational power and the complexity of the physics we are attempting to resolve. The transition from descriptive statistics to predictive physics hinges on accurately capturing the nonlinear interactions that govern the very first moments of stellar and planetary system assembly. Consider the role of turbulence, an omnipresent feature in astrophysical fluids, which is not merely a source of viscosity, but a driver of angular momentum transport, dictating the efficiency of accretion and migration. In the context of protostellar disks, this turbulence is generated by various mechanisms, including magnetorotational instability, where magnetic fields become wound up by the differential rotation of the disk, and hydrodynamic instabilities, where density variations lead to chaotic flows. The way these turbulent eddies mix and transport angular momentum across the disk is fundamentally scale-dependent. The physics operating on the scale of the disk itself, where planets form, must be seamlessly coupled with the physics operating on the scale of the stellar magnetosphere, where magnetic fields are anchored and exert their influence. The magnetic fields, which we have established as a crucial modulator of accretion and atmospheric survival, introduce another layer of complexity. Stellar magnetic fields thread the accretion disk, exerting a torque that can influence the disk's evolution, potentially channeling material and regulating the accretion rate onto the forming star. This magnetic braking mechanism, where magnetic field lines act as a brake on the stellar rotation, is intimately linked to the disk's viscosity. If the magnetic fields are strong and effectively coupled to the disk, they can mediate angular momentum transport more efficiently than purely hydrodynamic viscosity, leading to different migration rates and final orbital separations than predicted by purely viscous models. The interplay between the magnetic field topology, whether it is purely toroidal, poloidal, or a complex tangle of flux tubes in. The thermal pressure dictates how energy is dissipated and how material flows. For instance, in highly magnetized disks, the magnetic pressure can become comparable to the thermal pressure, fundamentally altering the equations of state and the stability criteria for gravitational collapse, pushing the system towards regimes where magnetic forces dominate thermal ones. When we turn to the formation of specific planetary types, the physics of solid accretion becomes even more critical. The condensation sequence is not just a temperature-dependent process. It is a chemical kinetic process occurring within a dynamic, chemically inhomogeneous environment. The presence of dust grains, which act as the seeds for planetesimals, is governed by the balance between aerodynamic drag, gas pressure gradients, and the sticking efficiency of the material. If the gas is highly turbulent, the dust particles experience chaotic velocities, potentially inhibiting the necessary gentle collisions required for sticking and growth, thereby favoring the gravitational instability pathway over slow core accretion in those specific turbulent regions. The resulting initial mass function of the protoplanetary system is therefore imprinted not just by the initial density profile, but by the specific turbulent cascade that occurred during the disk's lifetime. Moving deeper into the realm of numerical simulation, the next critical step involves resolving the accretion process itself with greater detail. We need simulations that can resolve the magnetic field lines down to scales where plasma effects become dominant, incorporating full non-ideal magnetohydrodynamics. This means tracking the evolution of magnetic flux through the disk, allowing us to quantify the magnetic torque exerted on the disk, and simultaneously tracking the thermal evolution of the gas, which feeds back into the magnetic field via ambipolar diffusion and ohmic resistivity. The challenge lies in the vast dynamic range. The disk spans from the stellar radius to hundreds of astronomical units, and the magnetic structures exist across an enormous range of scales, from the stellar surface down to the scale of the forming planet. Bridging this gap requires adaptive mesh refinement techniques, allowing the simulation to dedicate computational resources where the physics is most active at the interface between the magnetic field and the thermal gas. Furthermore, the long-term orbital evolution, especially the chaotic scattering events that generate eccentric orbits, requires incorporating the gravitational influence of the entire galactic environment. The local stellar density, the presence of nearby massive stars, and the gravitational influence of the galactic tidal field introduce perturbations that act on the nascent planetary systems. These external forces act as stochastic drivers, seeding the initial conditions that lead to the observed distribution of orbital parameters. To model this effectively, simulations must be extended to encompass larger volumes, moving from isolated systems to galactic-scale simulations, where the interplay between the star, its disk, and the wider galactic potential is explicitly calculated. This allows us to test whether the observed eccentricities are a consequence of internal disk dynamics alone, or if they are significantly influenced by external gravitational scattering events within the galactic neighborhood. The ultimate predictive power of this endeavor rests on developing robust, self-consistent physics that can handle these multi-scale, non-linear dynamics. We are not simply cataloging outcomes. We are attempting to reverse engineer the initial conditions from the observed distribution. This requires a framework where the initial density fluctuations, the magnetic field topology, and the thermal state of the molecular cloud are treated as the fundamental, probabilistic inputs, and the resulting planetary architectures are the emergent, predictable outputs. The next phase is the development of these integrated, high-fidelity computational tools, aiming to transform the statistical tapestry of exoplanet discovery into a deterministic physical narrative of cosmic emergence. This necessitates a deeper dive into the non-ideal effects that govern the coupling between the plasma and the surrounding environment, specifically focusing on the role of resistivity and the associated magnetic diffusion processes within the accretion flow. The ideal magnetohydrodynamics, which assumes perfect conductivity, breaks down when considering the kinetic effects that govern how magnetic energy is dissipated into thermal energy and how angular momentum is truly transported. The process of ambipolar diffusion, for example, becomes paramount in regions where the plasma is partially ionized, allowing the magnetic field lines to slip relative to the bulk matter, a process that is crucial for understanding the slow, dissipative evolution of the disk. This diffusion rate is directly tied to the ion-neutral friction, which depends sensitively on the ionization fraction and the scale length of the magnetic field structures, introducing a strong nonlinearity into the viscosity term that we previously discussed. If we neglect this non-ideal term, the predicted accretion rates and disk lifetimes become artificially sharp and unstable, failing to account for the gradual, diffusive smoothing of magnetic structures that occurs over astrophysical time scales. Consider the structure of the magnetic field itself. In the context of accretion, the magnetic field lines threading the disk are not simply passive tracers. They are active participants in the dynamics. Magnetic tension and pressure exert forces that compete directly with the gravitational forces and the thermal pressure. When the magnetic field is dominated by toroidal components, as is often the case in differentially rotating disks, the magnetic field lines are wound up, storing significant amounts of magnetic energy. The mechanism by which this energy is released, leading to accretion, is mediated by the magnetic stresses. The efficiency of this release is modulated by the magnetic diffusivity, which dictates how quickly magnetic flux diffuses across the disk, effectively mediating the angular momentum transport. A higher magnetic diffusivity implies a more efficient mixing and transport of angular momentum, potentially leading to faster accretion rates onto the central object, and consequently, different stellar magnetic field evolution histories. The transition between the ideal MHD regime and the resistive regime is not sharp, but gradual, depending on the local plasma conditions. In the hotter, more ionized inner regions of the disk, resistivity is high, and the system behaves more classically, allowing for rapid magnetic field diffusion. Conversely, in the cooler, denser regions where dust grains are forming, and the gas is partially ionized, ambipolar diffusion becomes the dominant mechanism for field evolution, effectively decoupling the magnetic field from the bulk flow on these scales. This scale-dependent physics means that a single, monolithic description of the disk is insufficient. We must treat the system as a continuum of dynamically distinct regimes. The thermal state, determined by radiative transport and viscous dissipation, feeds back into the magnetic field via the equation of state, creating a complex coupled feedback loop where thermal instability drives magnetic evolution, and magnetic evolution dictates thermal transport. Now, let us shift focus to the processes of solid accretion and planet formation, examining the interface between the gaseous dynamics and the solid component, with renewed emphasis on the turbulent environment. The sticking efficiency of dust grains, the prerequisite for forming planetesimals, is highly sensitive to the relative velocity distribution imposed by the turbulent cascade. If the turbulence is highly supersonic or exhibits extreme shear, the relative velocities between dust grains can be so large that the collision energy is insufficient to overcome the material's cohesive forces, leading to fragmentation rather than accretion. Conversely, in a moderately turbulent, subsonic environment, the chaotic motions facilitate the necessary close encounters and gentle sticking events that allow pebbles to coalesce into larger bodies. The characteristic scale of this turbulence, the Kolmogorov cascade, dictates the spectral distribution of these velocities, and thus the efficiency of dust growth, which directly sets the initial mass function of the protoplanetary system. This implies that the observed mass distribution of exoplanets is not merely a reflection of initial conditions, but a direct readout of the specific history of turbulent mixing within the disk. Furthermore, the vertical structure of the disk, the way density and temperature vary with height, plays a critical role in determining where these processes occur. The disk is not uniform, It possesses a complex stratification influenced by stellar irradiation and magnetic field geometry. The vertical scale height, $H$, dictates the characteristic length scale over which vertical motions are constrained, and this scale height, in turn, influences the scale separation between the disk dynamics and the magnetospheric dynamics. Simulations must resolve this vertical structure to accurately capture how magnetic flux is threaded through the disk layers, as the magnetic field lines are not simply confined to the midplane, but extend into the vertical dimension, influencing the magnetic pressure gradient and the vertical flow profile. The next computational step demands a focus on resolving the magnetic field topology, not just in terms of magnitude, but in terms of its connectivity and complexity. The magnetic field is expected to be highly tangled in the disk, especially in the regions where the magnetorotational instability is active, leading to a complex web of flux tubes. Analyzing this topology requires moving beyond simple toroidal or poloidal field assumptions and employing techniques that quantify the magnetic helicity and the degree of field line entanglement. This entanglement directly influences the magnetic braking efficiency and the resulting accretion history. If the field lines are highly tangled, the effective viscosity might be higher or lower depending on the specific geometry, requiring a simulation framework that can dynamically evolve and resolve these fine-scale magnetic structures without introducing artificial numerical dissipation. This transition from macroscopic disk dynamics to microscopic magnetic structure resolution is the core computational hurdle in unifying accretion theory with planet formation theory. This transition from macroscopic disk dynamics to microscopic magnetic structure resolution is the core computational hurdle in unifying accretion theory with planet formation theory. To tackle this, we must delve into the specifics of how magnetic topology influences the accretion process itself, moving beyond the effective viscosity approximations and embracing the full complexity of magnetohydrodynamics within the disk. Consider the implications of magnetic helicity. Helicity, which measures the linkage and twisting of magnetic field lines, is a conserved quantity in ideal magnetohydrodynamics, and its presence in a magnetized plasma implies that magnetic field lines are inherently non-trivial. When the magnetic field is highly helical, it suggests a degree of magnetic complexity that resists simple smooth diffusion. This complexity directly impacts how magnetic flux is advected and dissipated. In regions dominated by the magnetorotational instability, where magnetic fields are amplified and tangled, the magnetic pressure and tension exert non-axisymmetric forces that can channel the angular momentum transport in ways that are not purely governed by the simple $\alpha$ viscosity derived from a smooth, non-tangled field. We are not just interested in the magnitude of the field, but the geometry of the field lines threading the disk, as this geometry dictates the pathways for magnetic flux leakage and the resulting torque applied to the plasma. Magnetic braking mechanism, which drives accretion, is fundamentally linked to the magnetic field's ability to extract angular momentum from the rotating fluid. In the standard model, this extraction is mediated by magnetic stresses. If the field lines are highly tangled, they introduce magnetic tension and pressure anisotropies that complicate the notion of a single, coherent magnetic lever arm. A tangled field structure implies that the magnetic field is not simply aligned with the local rotation axis or the disk plane in a simple manner. Instead, the field lines weave through the plasma in intricate patterns. This weaving introduces magnetic reconnection events, even in the resistive regime, which act as localized, highly efficient mechanisms for dissipating magnetic energy and transferring angular momentum. These reconnection events, occurring on scales much smaller than the macroscopic disk thickness, effectively mediate the transition from magnetic energy storage to kinetic energy release, and they are intrinsically tied to the fine-scale magnetic topology. To model this, We require numerical methods capable of resolving these small-scale structures. Standard grid-based simulations often suffer from numerical dissipation that can artificially smooth out the very structures we are trying to investigate. Therefore, techniques that explicitly conserve magnetic helicity or employ adaptive mesh refinement that can resolve features down to the scale where ambipolar diffusion becomes dominant are necessary. We must move towards a framework where the evolution of the magnetic field is not just governed by the macroscopic equations of MHD, but by the interplay between the large-scale differential rotation, the vertical stratification, and the small-scale resistive effects occurring within the turbulent eddies. Furthermore, the coupling between the magnetic field and the thermal state must be handled self-consistently across all scales. The thermal balance, governed by radiative transfer and viscous heating, dictates the ionization fraction and thus the resistivity, which in turn controls the magnetic diffusion. This feedback loop necessitates a treatment where the equation of state, which links pressure, density, and temperature, is dynamically coupled to the magnetic field evolution. This is particularly acute in the transition zones, such as the interface between the hot, ionized inner disk and the cooler, partially ionized outer regions. Here, the scale length of the magnetic structures, which determines the relative importance of ohmic diffusion versus ambipolar diffusion, becomes a crucial local parameter. Magnetic field lines, threading through these differentially rotating layers, are subject to differential motion, which generates magnetic forces that drive the accretion flow, and these forces are modulated by the local plasma properties. The planet formation aspect, specifically the sticking efficiency, is also deeply intertwined with this magnetic environment. If the turbulence generated by the magnetorotational instability is strongly anisotropic due to magnetic tension, the resulting velocity field will not be isotropic, meaning the relative velocities of dust grains will be highly directionally dependent. This anisotropy directly affects the probability of sticking. Dust grains, being electromagnetically coupled to the ambient magnetic field, will experience forces that bias their trajectories. A highly tangled, strong magnetic field will impose constraints on the relative motion of dust, potentially suppressing the random, chaotic motions necessary for efficient sticking, favoring instead coherent shearing motions that lead to fragmentation or ejection. Conversely, in regions where the magnetic field is relatively weak or highly ordered, the kinetic energy of the turbulent cascade can be more effectively translated into the necessary small relative velocities for sticking. Therefore, the goal of the next set of simulations must be to map the evolution of magnetic helicity and field line entanglement as a function of the local thermal state and the scale separation between the turbulent eddies and the magnetic diffusion scale. This requires a multi-scale approach, where the simulation can simultaneously track the large-scale viscous evolution of the disk, the vertical stratification, and the fine-scale evolution of magnetic flux tubes, allowing us to quantify precisely how the magnetic field topology dictates the accretion rate and the subsequent assembly of solid components. This integration of scales from the macroscopic accretion rate down to the microscopic magnetic entanglement is the necessary step to bridge the gap between the physics of accretion and the physics of planet formation. This multi-scale integration necessitates a formalism that transcends the limitations of purely local approximations, demanding a framework where the non-ideal effects of plasma physics are woven directly into the geometric description of the accretion flow. We must move beyond treating viscosity as an emergent, phenomenological quantity, and instead derive the angular momentum transport directly from the magnetic stress tensor, accounting for the non-ideal terms that govern the magnetic field evolution. Consider the role of magnetic helicity not merely as a conserved quantity, but as an active thermodynamic variable influencing the efficiency of energy transport across the disk. Helicity flux, the rate at which magnetic helicity is transported, becomes a critical diagnostic for understanding how magnetic energy is converted into the kinetic energy driving accretion, and how that process is influenced by magnetic reconnection events occurring across various spatial scales. When reconnection occurs, it releases stored magnetic energy, and this energy release is channeled into bulk plasma motion, directly contributing to the viscous torque. The efficiency of this conversion is highly dependent on the topology. A field that is highly knotted allows for more complex, multi-scale reconnection pathways, potentially leading to a more efficient, albeit chaotic, angular momentum transfer, compared to a smoothly ordered field where transport might be dominated by simpler diffusion. The vertical structure of the disk, where the magnetic field lines are forced to thread through regions of vastly different plasma densities and temperatures, introduces further complexity. The ambipolar diffusion timescale, which governs the relative slippage between the ions and neutrals, becomes a scale-dependent regulator for magnetic diffusion. In the weakly ionized regions, such as the cooler midplane, ambipolar diffusion acts as a magnetic resistivity, allowing the magnetic field to diffuse more slowly. But this diffusion is fundamentally anisotropic, strongly dependent on the orientation of the field relative to the density gradient. This anisotropy means that the magnetic tension exerted along the field lines is not simply a scalar force, but has distinct components parallel and perpendicular to the flow, directly modulating the differential rotation. The accretion velocity, therefore, is not just determined by the balance of pressure gradients and centrifugal forces, but is intrinsically linked to the magnetic tension resisting the rotation. We are looking at a regime where the magnetic field acts as a mediator, imposing constraints on the kinematic possibilities of the fluid motion. Furthermore, the feedback from the thermal state must be explicitly integrated into the magnetic evolution equations. The equation of state, linking pressure, density, and temperature, must be solved simultaneously with the induction equation. The thermal energy released by viscous dissipation must be radiated away, and this radiation process itself is modulated by the magnetic field geometry, as the magnetic field can influence the opacity of the plasma, thereby altering the radiative transfer and the subsequent thermal structure. This creates a tight, coupled system. Magnetic topology dictates the flow dictates the thermal state, and the thermal state dictates the magnetic diffusivity. This self-consistent coupling is essential for capturing the full complexity of magnetothermal accretion. Now, let us pivot to the implications for the dust component, the crucial link to planet formation. The sticking efficiency, $\epsilon stick $, is not merely a function of the relative velocity, $v rel $, but is critically modulated by the magnetic field. Dust grains, possessing magnetic moments, interact with the ambient field through Lorentz forces. If the magnetic field is highly tangled, the magnetic pressure exerts a complex, multidirectional force on the dust, which can either promote the necessary relative velocity for sticking or induce disruptive magnetic torques that lead to fragmentation or ejection. Imagine a scenario where the magnetic field lines are highly twisted, creating strong magnetic tension that resists any motion that attempts to align the dust grains with the local field lines. This resistance acts as a magnetic brake on the relative motion, effectively suppressing the chaotic, random motions required for the sticking process. Instead, the system favors large-scale shearing motions dictated by the differential rotation, which, if the magnetic field is sufficiently strong, can lead to the formation of magnetic vortices or flux tubes that sweep dust grains along field lines, potentially leading to rapid accretion or ejection rather than gentle sticking. Conversely, in regions where the magnetic field is relatively weak or exhibits a more ordered, poloidal structure, the kinetic energy from the turbulent cascade can be more readily converted into the small relative velocities required for sticking. In these less constrained environments, the turbulence acts more like an effective viscosity, providing the necessary stochastic kicks to bring dust grains into contact and lock them together. The spatial distribution of this sticking efficiency across the disk plane will therefore be a direct map of the magnetic topology. Regions with strong, tangled fields will be zones of magnetic control, where planetesimal formation is suppressed or channeled along magnetic pathways, while regions with weaker or more ordered fields will be the nurseries for solid accretion. This requires a computational approach that can resolve the magnetic field structure down to scales where ambipolar diffusion becomes the dominant diffusive mechanism, and where the effects of magnetic reconnection are resolved dynamically. We are looking for a simulation that bridges the gap between the global disk evolution, which dictates the overall accretion rate, and the microscopic physics of magnetic energy dissipation, which dictates the local efficiency of angular momentum transfer, and ultimately, the assembly of planetary cores. The necessity is to embed the physics of plasma turbulence, magnetic topology, and dust dynamics into a single, unified framework, allowing us to observe how the magnetic skeleton of the accretion disk dictates the fate of matter and the emergence of solids. The final picture emerging from this integration will not be a smooth, purely viscous accretion, but a highly structured, magnetically regulated process where the geometry of the magnetic field is the primary driver of both fluid dynamics and solid accretion. This integrated view demands a fidelity in resolving the magnetic field structure that pushes current numerical capabilities to their limits. We must move beyond idealized, smoothly varying field approximations and confront the inherent nonlinearity introduced by magnetic field line evolution. Consider the resistive layer itself, the region where the plasma dynamics transition from ideal MHD behavior to resistive diffusion, and where the magnetic resistivity, governed by ambipolar diffusion, becomes the bottleneck for energy transport. In these weakly ionized layers, the magnetic field lines are not merely passive conduits. They are actively coupled to the neutral fluid motion through the ion-neutral drift, a process fundamentally tied to the scale separation between the plasma dynamics and the neutral fluid response. The anisotropic nature of this diffusion means that the magnetic field resists stretching along the direction of the field lines far more strongly than it resists motion perpendicular to them, introducing a directional memory into the disk's evolution that simple isotropic viscosity entirely misses. This memory manifests as a magnetic tension that resists the differential rotation, effectively creating magnetic braking that channels angular momentum away from the inner regions, feeding the accretion flow. The mechanism of magnetic reconnection, when occurring across these multi-scale structures, is not a singular event, but a continuous, stochastic process woven into the fabric of the disk. Small-scale current sheets, where magnetic gradients are steepest, become sites of rapid energy release, converting magnetic energy directly into thermal energy and kinetic energy of the plasma. If these reconnection events are distributed throughout the disk, they introduce a non-local transport mechanism for angular momentum that is inherently magnetic, bypassing the purely hydrodynamic viscous terms. The efficiency of this magnetic viscosity depends critically on the magnetic field geometry, specifically the degree of field line complexity. In highly tangled fields, the field lines are forced into a multitude of small loops and flux tubes, providing numerous sites for reconnection, leading to a high effective magnetic diffusivity that rapidly smooths out magnetic gradients and accelerates the viscous transport of angular momentum. This turbulence, driven by the magnetic field itself, acts as the engine driving the accretion, not just the macroscopic shear. When we introduce the dust, the transition from this magnetic kinematic framework to solid accretion requires understanding how the magnetic field mediates the turbulent cascade. Dust grains, being electrically charged, respond to the Lorentz force, experiencing forces that are intricately linked to the magnetic field topology. If the magnetic field is strong and highly organized, it imposes a strong constraint on the relative motion between the dust and the gas, potentially preventing the necessary chaotic relative velocities from being established for sticking. Instead, the flow is channeled along field lines, leading to coherent drift rather than random collisional sticking. However, if the field is tangled, the magnetic pressure exerts a complex, fluctuating force on the dust, generating the necessary stochastic velocity fluctuations that allow grains to overcome their initial inertia and settle into contact, facilitating the growth of planetesimals. This suggests a phase transition in accretion efficiency dictated by the magnetic state. Ordered fields favor magnetic channeling and transport, while chaotic fields favor the necessary kinetic stirring for sticking. Therefore, the simulation must track not just the magnetic field strength, but the evolution of magnetic helicity as a conserved or quasi-conserved quantity, and simultaneously resolve the microphysics of dust-gas interactions within this dynamically evolving magnetic environment. The resulting structure will be a tapestry where the accretion rate, the temperature profile, and the solid mass distribution are all inseparable consequences of the underlying magnetic topology and its dissipative mechanisms. The final observational signatures, whether in the emitted radiation or in the distribution of solids, will serve as indirect probes of this hidden magnetic skeleton, revealing the unseen machinery driving the birth of planets. Thank you for watching. If you enjoyed this story, please like and subscribe for more.